The celestial mechanics of the cosmos are precise, yet subject to violent disruptions. Imagine a sudden, cataclysmic gravitational interaction, perhaps with a rogue giant planet or a close pass by a binary star that wrenches Earth from its familiar orbit. The Sun, once a life-giving constant, rapidly recedes into a distant, diminishing star, its light fading to a pinpoint amongst billions. Ejection from the solar system transforms Earth into a rogue planet, adrift in the interstellar void. The planet's fundamental energy source vanishes. Without the Sun's radiant heat, surface temperatures plummet rapidly. The delicate thermodynamic balance that sustains liquid water and atmospheric stability begins an irreversible collapse into an alien frigidity. Initially, residual atmospheric heat and the planet's internal geothermal energy offer a temporary reprieve. Earth's molten core continues to generate heat through radioactive decay, maintaining a temperature gradient that slowly bleeds outward. This internal furnace, however, is insulated by kilometers of rock and only delays the inevitable deep freeze of the surface. As the surface temperature drops below freezing, the planet's vast oceans begin to solidify. Water molecules, losing kinetic energy, arrange into crystalline ice structures. This process starts at the poles and progresses rapidly towards the equator, encapsulating the entire oceanic surface in an ever-thickening shell, trapping gases and residual atmospheric moisture within it. The atmosphere, once a dynamic blanket, experiences a drastic change. Water vapor freezes out first, forming vast sheets of frost. Subsequently, carbon dioxide and other gases will precipitate, transforming into frozen solids. The once fluid gaseous envelope would thin dramatically, becoming a whisper of its former self, a mere vestige of a habitable world. This ejected Earth would not be unique in the galaxy. Countless rogue planets, free-floating through interstellar space, exist. However, Earth carries a unique legacy: liquid water, a dense atmosphere, and complex life. Most rogue worlds are primordial, gas giants, or ice balls, never having known the warmth of a star or the biological processes it facilitates. Despite the surface desolation, pockets of life could theoretically persist. Deep within the oceans, around hydrothermal vents, geothermal energy provides heat and chemosynthetic nutrients. The thick ice layer forming above would act as an insulator, preserving pockets of liquid water below, sustained by the planet's internal warmth and geochemical processes. For any advanced civilization, immediate survival would hinge on rapid geoengineering and deep underground habitation. Subterranean cities, powered by geothermal energy or advanced nuclear fusion, would become the new bastions of existence. These enclosed biospheres would require sophisticated life support systems to recycle air, water, and waste completely independent of the hostile surface. The engineering challenges are immense. Constructing sealed environments capable of withstanding the extreme cold and radiation of interstellar space necessitates materials science far beyond current capabilities. Heat must be meticulously conserved, and energy generation must be sustained for millennia. The focus shifts from harnessing external resources to optimizing internal efficiency and resilience. Orbital mechanics, once a guide for navigation, becomes irrelevant for surface dwellers. The planet's trajectory through the galactic plane is dictated by the gravitational pull of the Milky Way itself, a journey spanning eons. Without the Sun, Earth travels a dark, solitary path, its primary interaction with other celestial bodies limited to extremely rare and dangerous close encounters. Comparatively, interstellar travel for a human-crewed vessel necessitates similar sealed environments, but on a smaller scale and with propulsion systems. A rogue Earth, however, lacks propulsion. Its motion is passive, a cosmic drift. The immense mass of the planet makes any significant course correction an engineering impossibility, trapping its inhabitants on a fixed cold trajectory. The long-term atmospheric fate in a rogue scenario is critical. Without the Sun's UV radiation to drive photochemistry, the upper atmosphere's composition would slowly alter. Light gases might gradually escape into the vacuum, though the frozen surface and lack of solar heating would reduce this effect over time. The atmosphere would become a static, cryogenic blanket. Life inside the deep-sea vents or subterranean habitats would evolve in complete darkness, adapting to chemotrophic energy sources. Photosynthesis, the foundation of Earth's surface biosphere, would cease. The food web would collapse to its most basic, reliant on chemical gradients and geothermal energy, fostering unique extremophile ecosystems isolated from the surface world. However, even with advanced technology and subterranean havens, resources are finite. The internal geothermal heat of Earth, though vast, slowly diminishes over astronomical timescales. Nuclear fuel eventually depletes. Without a continuous external energy source, the long-term prognosis for complex life on a rogue planet, however resilient, trends towards an inevitable entropic decline. The planet's core, though molten, would continue to cool. This gradual thermal decay would eventually lead to the solidification of the outer core, weakening or extinguishing the geodynamo. With no protective magnetosphere, Earth would be exposed to the full spectrum of interstellar cosmic radiation, a constant bombardment further threatening any surviving surface or near-surface life. The long-term existence within subterranean habitats presents an unprecedented sociological experiment. Generations born and raised beneath kilometers of ice and rock would know only the engineered light of their enclosed world. The concept of a vast open sky of stars and a sun would become an abstract historical fact, perhaps relegated to myths or ancient texts preserved in digital archives. Maintaining the complex machinery necessary for survival against the entropy of time is a perpetual struggle. Reactor components degrade, air purifiers clog, and water recycling systems face cumulative stress. Continuous innovation and meticulous maintenance would be paramount, consuming a significant portion of societal resources, pushing the limits of available raw materials. The psychological impact of perpetual darkness and confinement on the human psyche is profound. Without natural circadian rhythms and the vastness of the natural world, mental health challenges would proliferate. Isolation, both physical and cosmic, fosters a unique form of existential ennui, where the very purpose of continued survival must be constantly reaffirmed. Over astronomical timescales, even internal geological activity would wane. As the molten core slowly solidifies, volcanic activity and hydrothermal vents diminish. The very energy sources sustaining deep-sea ecosystems and potentially powering subterranean cities would eventually dwindle, posing an ultimate expiration date for all earthbound life. The surface, once vibrant, becomes a monument to a forgotten age. Its atmosphere, largely frozen onto the planetary crust, would be too thin to buffer any impact events. Without a magnetic field, the planet is a naked target, its surface scarred by high-energy cosmic rays and the occasional micrometeoroid, leaving no evidence of its once flourishing biosphere. Any surviving subterranean life forms, including genetically isolated human populations, would undergo significant evolutionary pressures. Adaptations to low-light, closed-system environments and altered atmospheric compositions would drive biological divergence. The organisms that once thrived on a sunlit planet would be irrevocably altered by the profound cosmic shift. The prospect of encountering another celestial body in the vastness of interstellar space is astronomically remote, yet not impossible. A rogue Earth might pass near another dark star or free-floating planet, resulting in gravitational perturbations, seismic activity, or even a direct collision, a final catastrophic end to its solitary journey. The planet's journey would be a slow drift through the galactic halo, eventually reaching regions where even the distant light of other stars is almost imperceptible. Earth would become a true dark wanderer, its internal warmth its only source of light and energy, a silent testament to a world that lost its sun. The knowledge of the cosmos itself would degrade. Future generations confined to their subterranean enclaves might lose the observational data of distant galaxies and nebulae. Their understanding of the universe would be limited to theoretical models and historical records, the direct experience of the vast cosmos rendered impossible. The inexorable cooling of Earth's interior would gradually diminish geothermal activity. Hydrothermal vents, once teeming with chemosynthetic life, would slowly become inactive. The last vestiges of liquid water, insulated beneath kilometers of ice, would eventually freeze solid as the internal heat gradient flattens, extinguishing these isolated biospheres. Without the planet's internal dynamo generating a magnetic field, the core would cease to protect Earth from high-energy cosmic radiation. the planet would be subjected to the unfiltered bombardment of interstellar particles, slowly eroding any remaining trace atmospheric gases and sterilizing its exposed surface, ensuring complete surface desolation. The water cycle, a fundamental process for Earth's habitability, would utterly cease. With no solar energy to drive evaporation, all water would remain in its frozen state. There would be no clouds, no precipitation, no liquid flow across the surface. The planet would become a perpetually frozen sphere, its once dynamic hydrological system entombed in ice. Plate tectonics, driven by the convection currents within Earth's mantle, would also eventually grind to a halt. As the planet cools and solidifies from the core outwards, the mantle's viscosity would increase. Volcanic activity, mountain building, and continental drift would cease, rendering the planet geologically inert and seismically stable in its frigid journey. The final evolutionary outcome for any surviving life, even in the most protected subterranean pockets, would be ultimate extinction. While extremophiles can endure incredible conditions, the finite energy reserves and the slow but inevitable thermal decay of the planet's interior ensure that even these resilient forms of life face an expiration date, a cosmic-scale energy crisis. In its rogue state, Earth would resemble a cold dwarf in the cosmic typology. It would share characteristics with other dead worlds, tidally locked moons far from their gas giants, or exoplanets that have been ejected from their home systems. Yet Earth's unique history as a vibrant, life-sustaining planet would set it apart, a ghost of habitability. The absolute silence of the interstellar void would encompass Earth. No atmospheric sounds, no wind, no crashing waves. Only the subtle vibrations from within the planet's cooling crust would persist, alongside the occasional distant flicker of light from an unimaginably far-off galaxy, a universe indifferent to Earth's cold, solitary transit. The sheer material longevity of Earth itself means its physical structure would persist for eons, even as all biological and geological activity ceases. It would become a colossal, inert artifact carrying the fossilized records of its vibrant past, a frozen library drifting through the cosmic currents, a testament to what once was. This cold, dark voyage represents the ultimate isolation. The concept of home would be redefined within claustrophobic havens, while the boundless, starless expanse outside represented only an insurmountable, lethal barrier. The very perception of space would shrink to the confines of a self-sustaining artificial environment. The memory of the sun, once a universal constant, would fade from collective consciousness over countless generations. Astronomical phenomena, once observed and studied, would become theoretical constructs as the true appearance of celestial bodies remains hidden behind the perpetual night and the planet's thick ice shell. The cosmic perspective would fundamentally shrink. Over vast stretches of time, the Earth's atmosphere, already significantly thinned and frozen, would continue to bleed into the vacuum. Solar winds no longer existed to push it, but the planet's reduced gravity, due to the loss of a magnetic field, would allow lighter gases to slowly escape. The residual atmospheric pressure would diminish to near vacuum levels. The very definition of time would shift for any surviving civilization. Without the diurnal cycle, without seasons, without orbital periods, time would be measured by the relentless ticking of artificial clocks and the slow internal decay of their world. A deep, unchanging stillness would define existence, punctuated only by engineered routines. As Earth continues its journey, its surface would accumulate a layer of micrometeorites and cosmic dust, a slow, continuous accretion of interstellar debris. This material would blanket the frozen landscape, further obscuring any remaining geological features and cementing the planet's transformation into a true rogue wanderer. The ultimate fate of a rogue Earth is a slow, entropic decline into cosmic quiescence. Its energy dissipates, its internal warmth fades, and its geological and biological processes cease. It becomes a frozen dark sphere, a colossal tomb drifting through the galactic void, indistinguishable from countless other dead worlds. This ejected planet, once a vibrant oasis, offers a profound contrast to the life-sustaining worlds tethered to their stars. It highlights the precarious nature of habitability, a delicate balance maintained by stellar proximity and internal planetary dynamics easily shattered by cosmic chance. Life, once abundant, becomes a fleeting, precious anomaly. What does this ultimate cosmic isolation imply for the resilience of life itself? How long can biological systems, however complex or technologically advanced, defy the fundamental laws of thermodynamics when severed from their primary stellar energy source, drifting endlessly through the indifferent, silent expanse of interstellar space?